Hello once again. So welcome to a fifth lesson on quadratics. This last lesson we looked at modelling with quadratics, and this lesson we're going to do more on that subject too. The main reason being it links into lots of questions. I've already seen 2 exam questions which were lots of marks on this for the pure side of the course, and as well as this, because mechanics and objects falling under gravity follow a quadratic path, it is massively important not just in the pure side of the course but also the mechanics. So understanding quadratics and modelling with quadratics is crucial. So before we get started on some more modelling problems, I have 4 warm-up questions for you. Here they are. So if you could have a go at these first and then check your answers after using this video, that would be awesome. So have a go at them first, and then only after you've tried them, have a look at these solutions. So here's the answer to question 1. So for question 1, we need to find the value of 16 to the power minus 3 over 2 without using a calculator. So there's a few ways of tackling this one. What I'm going to suggest is we can use the power of a power law of indices and say that 16 to the power minus 3 over 2 is actually the same thing as 16 to the power of 3 over 2 to the power minus 1. Using the power of a power rule, to the power 3 over 2, then to the power minus 1, we multiply the powers, and this is the same as minus 3 over 2. So now what we can do is think about 16 to the power 3 over 2. We could leave this to the power minus 1 until afterwards. So if it's a fractional power, the bottom bit of a fraction, the denominator, tells us what root we're taking of this number. So because we're talking halves, this is square roots. And so we can think of this as being 16 square rooted and then cubed. And then all of that to the power minus 1. So the square root of 16, we know that that's 4. So this is the same as saying it's 4 cubed to the power minus 1. 4 cubed is 64, so this becomes 64 to the minus 1. And anything to the power minus 1 is the reciprocal of itself. So this is the same as being 1 over 64. And so that's question 1 solved. Question 2. We need to use the property of the discriminant for this one. So we're told that we have an equation kx squared plus 12x plus k equals 0, where k is a positive constant, has equal roots. Find the value of k. So because this quadratic has equal roots, that implies, that is telling us that the discriminant, which is this capital delta symbol, which to remind you is b squared minus 4ac, that must be exactly equal to 0. So that's a case of us thinking, well, what is our a, what's b, what's c? And so a is just the coefficient of the x squared. So a is k. B is the coefficient of the x term, so b in our case is 12. And c at the end here is also k. And so if we just substitute these values into b squared minus 4ac, we're going to get that 12 squared minus 4 multiplied by k again is equal to 0. Again, just colour coding it in case you want me to. So 12 is b, a was k, as was c. So simplify this now. 12 squared is 144, and 4 multiplied by k is the same as 4k squared. That equals 0. Now, each of these numbers has a common factor of 4. So we can divide through all of this equation by 4 to arrive at 36 minus k squared equals 0. Make k squared the subject, we can see that k squared must be 36. Therefore, k normally would be saying k is plus or minus the square root of 36. However, we're clearly told here that k is a positive constant, so we have to ignore the minus square root option. So k must be the positive square root only. So k is just the square root of 36. Therefore k has to be 6, because k was defined as a positive constant. If it just says find the values of k and didn't mention this, we'd have to be saying that k is plus 6 or negative 6. Question 3, more of a test that you've understood the quick trick for doing these types of questions. Simplifying this should take you all of 5 seconds once you spot what's happening here. In terms of spotting what's happening, this is essentially just difference of two squares. A plus b brackets a minus b. And so because this is difference of two squares, all we have here is it's going to be 3 times 3, which is going to be 9, then root 5 times root 5, which is 5, and subtracted. And so this is going to be 9 minus 5, which obviously is just 4. Question 4, we have this quadratic function here, which has a maximum at minus 2, 8, and a root at x being minus 4. So it says find an equation of this quadratic, and to give your answer in the form y equals ax squared plus bx plus c, where a, b and c are real constants to be found. So using what we've talked about previously in terms of different forms of quadratics, we can use the form a brackets x minus h squared plus k. We can use the vertex form of the quadratic. The vertex form is essentially the completed square form. And if you remember, the completed square form, this form, tells us the turning point, either a maximum or a minimum. So we're using this because we are told what the maximum is. So if you remember, this h letter here relates to the value of x at the turning point. So for our case, that's going to be minus 2. And the k relates to the y coordinate at the turning point. So in our case, k relates to 8. And so we can just sub in these values to work out an equation for this quadratic. So we next have y equals a brackets x minus 2, just be careful there, squared, and then plus 8. In other words, the equation of it is y equals a brackets x plus 2 all squared plus 8. That's not enough because we still need to work out what a is. And so we're told next that it has a root at x equals minus 4. So we're only told one root, but actually this is enough. A root is where the curve crosses the x-axis. So where it crosses the x-axis, we know that y is equal to 0. And so what we've actually got here, in a sense, is two values we can substitute in to this expression, this equation rather. So we know that x is minus 4 and y is 0, so we can substitute these conditions in. So if we now sub in that x is minus 4 and y is 0 at the root, we can then work out what this value of a must be. So y is 0, then a, sub in minus 4 for x, so minus 4 plus 2 all squared plus 8. So 0 equals, well, minus 4 plus 2 is minus 2, then minus 2 squared is minus 2 multiplied by minus 2, which is positive 4. So this is a multiplied by 4, which is 4a plus 8. Not hard to rearrange that and solve for a. You should realise that a has to be therefore minus 2. So then we have that y must equal minus 2 lots of x plus 2 squared plus 8. But this question is asking for our answer in this form here, y equals ax squared plus bx plus c. This is in completed square form, we need the answer in expanded form. So let's expand this out now. So what we have next is that y equals minus 2 lots of this all squared. So that's going to be x squared. Multiply each term and double it. So 2 times x times 2, that gives us 4x. Square the last term, so 2 squared is 4. And finally this plus 8. Next, multiply by minus 2, so we have minus 2 lots of x squared, minus 8x, minus 2 times 4 gives us minus 8, then plus 8, so this minus 8 and plus 8 will cancel, therefore our equation in expanded form is just minus 2x squared minus 8x. And so we've now solved this one. And so in our case, A is minus 2, B is minus 8, and C is actually 0. But this is still in the correct form, so we've done all the warm-up questions now. So moving on. So what you need to be really skilled at is going from one form of a quadratic to another. This is how the examiner likes to try and catch you out and just test that you're really masterful at swapping from factorized form to expanded form to vertex form. So I've just put this here in a little bit on your notes. So in terms of the different forms, the factorized form of quadratics allows us to see, if you like, the solutions by inspection, whereas the completed square form, which I sometimes call vertex form, allows you to inspect the turning point of the curve by just looking at the equation of it. So therefore it's absolutely crucial that you obtain as much practice as you possibly can in switching from one form to another. And this is what this next activity is about. So in your notes, for the boxes below this bit in your notes, you need to rewrite each quadratic function in expanded form into factorized form and then vertex form. Don't use a calculator. You can use a calculator to check if you like, but don't use a calculator to do the working. So I want you to have tried these first before looking at my solutions on this video. Okay, so once you've had a go, I'm now going to show you how you could have arrived at these solutions, swapping from factorized and then vertex form. So let's now have a look at question 1, part A and B. So for 1A and B, the function is f of x equals x squared minus 4x. I've color-coded this in green because this one is relatively straightforward. The next one's a yellow or amber for sort of in the middle, and the final one in red, which is much harder. First of all, this is quite easy. A common factor of x, so this simply just becomes x brackets x minus 4. Here we can complete the square, and so we put the x in the brackets. We half the coefficient of this x here, so half of minus 4 is just minus 2. We square all of that, then minus off this term all squared, so we subtract off 4. So that's question 1, part A and B complete. Question 2, parts A and B, slightly harder, but not too hard. So for factorising this one here, we need to think of two values which multiply together to give us minus 28, and when we add them together, that needs to give us 12. And so two numbers that multiply to minus 28 and add to 12, with a bit of thinking, you should find that they're 14 and minus 2. And so this one's going to be x plus 14, x minus 2. Over here, completing the square, the x squared, we just put the x in the brackets, half the coefficient of x, so half of positive 12 is positive 6. We square all that. We subtract off this thing here all squared. So we subtract off 36, and of course subtract off this 28 too. Simplify it, which we can. We get x plus 6 all squared, and minus 36 minus another 28, that's the same as saying minus 64. Question 3, going a bit harder now. So, a little trick here. I'm hoping you'll spot, really important actually, that this has a common factor of 5 for each of these things. So let's just take out that 5 straight away. We then get x squared plus 5x minus 6. So we can factorise what's inside these brackets here and leave this 5 alone on the outside. So in these brackets, just need to find a pair of numbers that multiply together to give us -6, but when we add them together, it gives us +5. And I'm sure you'll see those two numbers are going to be +6 and -1 in any order. So if you put -1 first and then +6, that's absolutely fine. Do similar for writing it in vertex form, but we only need to factorise out the 5 from these bits here. We can leave this constant term on its own when we're completing the square. And so if we write this as 5 brackets x squared plus 5x first, and leave that -30 on its own, we can now complete the square on this x squared plus 5x. So x squared, in fact what I'm going to do, I'm going to put this in bigger squared brackets, because we're going to have brackets inside brackets, which can be slightly confusing. So I'm going to put this in big squared brackets actually. So in brackets we're going to have an x, half the coefficient of this x here, so half of 5, we're going to have 5/2. All of that squared. And then we subtract away this 5/2 all squared. So square the top, we get 25. Square the bottom, we get 4. And again, this -30 at the end. So third step, multiply all of this by 5. So expand this out, we get 5 lots of x plus 5/2 squared. This times by 5 is going to be -125/4. And a bit of non-calculator practice for you. -30, well 30 is the same as 120/4. Okay? So for this last step now, we can put this constant term under a common denominator of 4, and we end up with 5 lots of x plus 5/2 all squared minus 245/4. Question 4, again, just inspect to see if there's a common factor in all of these terms. There's a common factor of 3. So for this one, factorise out the 3. You'll then arrive at x squared minus 18x plus 32. This bit inside the brackets will now factorise quite nicely. So two numbers that multiply together to give us 32, yet when we add them give us -18. Those numbers would be -2 and -16. Likewise over here, we can just factorise out this part. We can leave this 96 on its own. So we're going to have 3 lots of x squared minus 18x plus 96. Complete the square on this bit. So in the brackets goes the x, minus 18, half that becomes -9. All of that squared. Then we need to subtract off the -9 all squared. So -9 times -9 is positive 81, so we subtract off the 81. And again then plus 96. Now we can multiply all of this by 3, so we have 3 lots of x minus 9 squared. 3 times -81 is -243, then plus 96. Final step, just neaten this up slightly. We're going to have 3 lots of x minus 9 all squared. Then -243 plus 96. Maybe just add 100 onto this. That'll give you -143. And subtract off 4, because 100 was 4 too much. -143, sorry, minus another 4. That's going to be -147. And again, if you're unsure or a bit nervous, do check on a calculator. But try and do as much of this as if you can without. Lastly, question 5 in red, because this is quite a bit harder and easy to make mistakes. This one here has a common factor of -2. So if I factorise out -2, it makes it easier because this x squared term now becomes positive, so it's more familiar to us. So divide through all of these by -2. So 18 divided by -2, that's going to become -9x. The -40 divided by -2 gives us +20. So leave this -2 on its own. Two numbers that multiply to 20 and add to -9, they're going to be -4 and -5. Likewise here, we can factorise out the -2, and we get this, and we can leave that -40 on its own. Complete the square on this bit. Inside the brackets goes the x. Half -9 is -9/2. Square all of that, and subtract away this -9/2 all squared. Well, 9 squared is 81, 2 squared is 4. And we still have this -40 at the end. Expand this out, multiply through by -2. So we have -2, brackets x minus 9/2 all squared. -81/4 multiplied by -2 gives us positive 81/2. Then this -40 I'm going to rewrite as -80/2. 80 divided by 2 is obviously 40. And the final step, neaten this up, -2 brackets x minus 9/2 all squared. 81 halves take away 80 halves, we're just left with positive 1/2. And so that section of the notes is now done. Alright, so let's now have a look at a real worked example which came up in a past paper which was sat. It was a 7-marker as well. So these quadratics questions where you model with quadratics, they're no small fry marks. They are really worth mastering. This was 7 marks, which is an awful lot for just one topic really. So this one here says, you've got figure 1, which is a graph showing the trajectory of a rugby ball. You need to know as well by the end of year 13 that any projectile, if it's acting under gravity, will follow a parabolic curve. In other words, it's going to be a quadratic path. So you've got the height of this ball above the ground, which is been given the letter h. It's been plotted on a set of axes where the horizontal axis is x, and it's measured from the point where the ball is kicked. So when x is 0, that's the place where the ball was kicked from. The ball travels in a vertical plane. Now all that means is, if you imagine an invisible vertical upright pane of glass, or something like that, the ball is travelling in a straight line in one sense of a word. So it's not going to be swerving in the air, it's not bending, it's not curling, it's just going straight from point A to B. It might be going up and down, but it's going in a straight horizontal line, where it's like a horizontal vertical plane. The ball reaches a maximum height, we're told, of 12 metres, and it hits the ground at a point 40 metres from where it's kicked. Part A asks us to find a quadratic equation linking this h with x that models this situation. Now there's two main ways you could do this. So I'm going to first of all mention method 1, using the root form of the equation. So root form just means working out this equation based on where it crosses the x-axis. So we can see already that it crosses the x-axis, well, it's at the x-axis at the origin, and also over here where the ball lands. And we're told as well that the ball hits the ground at a point 40 metres from where it was kicked. And so essentially what we're told is this coordinate here is where x is 40. Here x is 0. So going back to previous lessons, the root form of any quadratic is normally y, but in this case it's going to be h, then some multiplicative constant, which I'm going to call capital A, then x minus one root, so x minus 0, x minus a second root, x minus 40. But of course, x minus 0 is just x, and so that's the same as saying it's capital A, x minus 40. But that only gets us so far. We need to know something else to work out what this capital A is. And we can do that, luckily, because we're also told that this ball reaches a maximum height of 12 meters. What we also need to know and remember for any quadratic curve, for any quadratic function, if we know the roots, the turning point is always halfway in between the roots. And so the maximum of this ball will happen halfway between 0 and 40 by the symmetry of the parabola. And so the maximum height will be when x is 20. So I'm just going to sketch this in here. So where x is 20, that's when the height is 12. So let's just add this into our diagram, like so. So 20, h is 12. So we can now substitute this in to this form. So if we sub the coordinates 20 and 12 in, what we're going to get is that the h, the height, is 12 when x is 20. So ax is then a times 20. So we have 20a, then brackets 20 minus 40. So this can be neatened up. And so 12 is going to equal 20 times, this is minus 20, so it's going to be minus 400a. So now if we divide through by minus 400 rather, we can work out that a must be negative 0.03. We can now substitute this value of a back into this equation here to work out the full simplified equation for h. So therefore, h equals a, which is minus 0.03, x, brackets x minus 40. That is the equation of this quadratic that maps h and x together. Another method we could have used is going for the vertex form, the completed square form of this parabola. So we could have just jumped straight in and spotted about this maximum height. So the ball reaches a maximum height of 12 meters. So using the idea that it's at the maximum halfway between the roots, and so we know now that this is 40 and that this is 0. So like I mentioned before, we can work out from this information that the maximum height is reached when the ball is 20 meters away from where it was kicked. So if we just substitute in those conditions, so it's going to be at a maximum at 20, sorry, a maximum where x is 20, and that maximum height is 12. So if we can recall from the previous lesson what the vertex form of a quadratic is, it's capital A, where A is some multiplicative constant, brackets x minus h squared plus k, where h is the x-coordinate of the turning point and k is the y-coordinate of the turning point. So just substituting those values in, we have A, brackets x minus 20 squared plus 12. This time we need to substitute in another point. So whereas before we substituted in these two values, 20 and 12, we now need to substitute in a root. And so we can either substitute in 40 and 0, or if we wanted, we could just substitute in the origin, 0, 0. I think 0, 0 would be an easier one to pick. So when the height is 0, x is 0. So that becomes A, brackets minus 20 squared. Well, minus 20 squared is 400. So then we have 0 equals 400A plus 12. So subtract 12 from both sides, we get minus 12 equals 400A. Divide through by 400. A must be, once again, as we saw before, minus 0.03. So the equation for h, now we know that A is minus 0.03, h is minus 0.03 lots of x minus 20 all squared plus 12. So a differently written form to method 1, but method 1 and method 2 are exactly the same thing, just written in different ways. So that's part A done. We found a quadratic equation. Either one or the other would get you full marks. Part B, we're told now the ball passes over a horizontal bar of a set of rugby posts that's perpendicular to the path of the ball. The bar's 3 meters above the ground. So we use the equation from part A to find the greatest horizontal distance of the bar from 0. So let's just remind ourselves of the equation or equations we got from part A. So here they are. Either one would do. We can now also add in this information about this horizontal bar. So we're told about this horizontal bar here. Okay, and we're told it's 3 meters from the ground. And so if I just imagine this horizontal bar on this diagram of ours. So the maximum height of a ball is 12. So if that's 12, that's about 6. This is about 3. Just estimating here. Don't need to measure it exactly. So this is the bar. The height of the bar anyway. I'm not saying it's going to be a 40-meter long bar, but this is the height of the bar. And what we're after is the greatest horizontal distance of the bar from 0. So the ball passes over. So in other words, when the ball reaches this bar, the ball has to be higher than the bar itself. So we can work out what the value of x is, where the ball would cross the bar. And then from that, that tells us both the first point, the ball would be crossing the bar, and the second point on the way back down. So as long as the ball is over this line, then the ball passes over. So because we want the greatest horizontal distance of the bar, this is the shortest distance, this is the greatest, and so we're actually after, in particular, this value here. So we're just going to set h equal to 3. And so this height is 3. So we'll just set h equal to 3 because we're told that this bar is 3 meters from the ground. So I'll just color code this just so you know where the information is coming from. So we can use either one of these equations. It doesn't matter which one you use, you'll come to the same conclusion, but I personally think this equation is the easier one to go for. And so let's pick this one here. So we just sub in h is 3 and then solve this equation. So 3 equals minus 0.03x brackets x minus 40. We can expand this out now. So we get 3 equals minus 0.03x squared. And then minus 0.03x multiplied by minus 40. If you use your calculator, that comes out as positive 1.2x. We can now rearrange this into the standard form of a quadratic, set it all equal to 0, and then use the formula to solve it. And so we then get 0.03 x squared minus 1.2x plus 3 equals 0. So if I just take this to the other side and solve it. So we then have that x must be plus or minus a. Sorry, I can't remember the bloody formula. I'm miles away. So x equals minus b, so minus 1.2, that's positive 1.2. Plus or minus the square root of b squared. So b is minus 1.2. So that squared is just going to be 1.2 squared. In fact, it's a minus, doesn't make any difference. When we square it, it comes out negative. Positive, sorry. And then minus 4 times a, which is 0.03, times c, which is 3. and all of that is going to be divided by 2 lots of A, which is 2 lots of 0.03. So let's see what we get. I'll also show you how to do this on the class whiz in the simpler way. So let's just clear this off the screen. So we've got 1.2, because it's minus 1.2, then plus the square root 1.2 squared minus 4 times 0.03 times 3, all of that divided by 2 multiplied by 0.03. So first one we get is 20 plus 10 root 3, which is 37.3 meters. The second root we get is this minus square root option. So if we just go back to the calculator, we don't need to erase everything. We can press this button here and toggle along. Just delete the plus, type in the minus, press equals again, and S arrow D to get it into a decimal. This 1, 2, 3 significant figures would be 2.68. Now we want the greatest horizontal distance of the bar, so this is the shortest. This relates to 2.68. This one up here is 37.3. So because we want the greatest horizontal distance, we're going to keep this one and we're going to reject this one. So our answer we're going for is this one here, 37.3 meters. Now I did say I'd show you how to do this on a class whiz. So if I just go back to this equation here, we can use our class whiz to smash this in a matter of seconds. So if we press menu and scroll along until we get to equation / func, press equals, option 2, because a quadratic is a polynomial, so press 2, and degree 2, because we have a squared term as the highest power, so press 2. Now we type in the parameters. So here A is 0.03, press equals. B is minus 1.2, so type minus 1.2 and press equals. And C is positive 3, so type in 3 and again press equals. We then get 10 plus 10 root 3, which is what we had here. Press equals again. We get the other root. Press S arrow D. We can see that this is 2.68, which we got from before. But that is clearly much easier than what we did using the quadratic formula. So although it's important to know how the quadratic formula works and to be able to use it, this class whiz is one heck of a powerful tool. So definitely make sure you can master yours. So let's move on. So what we've got here is part C, giving one limitation of a model. So based on the model we had, any reasonable criticism will do here. So any reasonable thing you can say where it's not going to be entirely accurate. So what springs to mind? You could put any one of these following suggestions. The ground is modelled as being perfectly horizontal. No pitch, no matter how good it is never going to be perfectly horizontal. It's always going to be going either slightly uphill or slightly downhill. Even if it's only like a couple of centimetres, that will affect the accuracy to some extent. Another thing you could have said is you're assuming no air resistance. Air resistance, no matter how small, does come into play, especially the windier the day is. So because there will be air resistance, it won't be a perfect parabolic path. Something else we could mention is we're assuming here the ball doesn't curve in the air. So for example, if spin's put on the ball, it won't be moving in a vertical plane. So we could have also said we're assuming it moves in a vertical plane. It's not going to move in a perfect vertical plane. It could bend, swerve, either because of the wind or the way the kicker has kicked the rugby ball. Another thing we could say, we're assuming the bar is a very thin line. So we're saying that it travels over a bar where the goal is. So using this model, if it were say a millimetre over, we'd say it crosses the bar. But actually this bar isn't going to be a millimetre thick. It's going to be having a significant thickness. So that is something which is a slight simplicity of the model. The actual real life situation would be more complex than how we're modelling it. Something else we could have mentioned, very similar to this one about the ball curving, we're assuming the ball has no spin. If a ball has spin on it, rugby balls often spin through the air, that would affect the air resistance in a very complex way and would mean our simple model doesn't quite match up to reality. So we're not saying our model's useless, we're just saying it's far from perfect. So any one of those, or any other similarly obvious common sense suggestion, would give you the extra 1 mark for part C. Now it's over to you. So there's a few questions in particular on mixed exercise 2 which are based on modelling quadratics in context. Those questions are 7, 11 and 14. So for mixed exercise 2, if you can try those 3 questions for me, that would be fab. Check your answers using the back of the book. If you're not sure how to get the solutions correct, either ask a classmate or come and ask me, either in lesson, on an email, or in this comment section in the video. Thanks for listening once again, and I hope to see you all soon.